刚刚没录吗？Okay, fine. Let's restart. So for who there for the ones who are looking at the recorded videos, so we are very sorry for that. We forgot to video it, record it before. So it's about half an hour. So it's not so important. Okay, so you can, if you have problems with the toric model, you can refer to many excellent books or videos, anything. I will touch them after the class. Okay, so let's restart. So what do we want to do? Let me see. Okay, I think there are some more observations to get some. Yeah. Here we want to get the wave functions. So we need some observation. The first is that we can how to say, we can choose a basis. Okay, so now we choose a basis of sigma x on a set I to be plus and minus. Okay, and in this picture, I think it plots the ones with if the sigma x is the eigenvalue of sigma x is -1, there is a red link, and otherwise or other is +1. So now let's see. So we call that we have the AV operator, and it is 4 sigma x times together on the vertex. So if there is some endpoints of the red string, so this AV operator should be -1. So this is not allowed for the ground state. So all the configurations will only the closed streams are allowed. Okay. Now another thing is that the BP operator can deform the red loops as we know in the quantum mechanics. So we act a sigma z on the eigenstate of the sigma x. It will flip it like this. So if you forgot about this, you can write the sigma x, this eigenstates like this, and you multiply it by the sigma z, the 1 - 1, and you'll find that it actually flips this. Okay. So what does this mean? It means that, for example, in this picture, the B, and we have a plaquette. There is a straight red line, and if we multiply a BP operator, and every link around this plaquette will be flipped, and the red line will be deformed. So this means that the this A and B configurations, they are actually equivalent. So in the sense that all the topologically equivalent loops configuration will give the same coefficient in the following wave function, the linear how to say, linear linear proposition, position. I forgot that English word. Oh, superposition. Yeah, the linear superposition. Okay. So, and from topology, for example, if we are on the torus, we have 4 different uncontrollable loops. Oh no. How to say? Topology, we have. Okay, so basically speaking, it's we are compute this homology class, and the input is the torus. Yeah, it's one. Groups, but I don't know exactly.
One input is the theory and one input is the actual geometry request. So you will output like.
But the question is how do we compute that? So in general, we have a systematic computation in math to about these problems, these questions. So yeah.
No. You can write the H1 as torus, you can write T2 and S1 times S1. And then you can divide this into 2 parts. One is H1 S1, V2 and times the other H1 S1.
So S1, so H1 S1 Z2 is Z2.
So,
okay.
So when all your space graph products, all the this can be true in the homotopy. It can be true in the homotopy. Remember, we can divide the chi one T2 into how to do it. I mean, if I just want to get some intuition from this equation, so the left hand side, your input is some geometry and your gauge group. And
I don't know whether it is gauge group.
So is there any like simple intuition from this equation? Somehow
the intuition is here, up here. So it is I think it is some configurations like this. So the phi 0, 0 is nothing. It's a contractible loop, and the phi 0, 1 is the loop in the big circle of the torus. And I think the phi 1, 0 is the small circle of the torus, and the phi 1, 1 is not phi. It should be psi.
Psi loop. Phi 0, 1 just x direction, and 1, 0 is a y direction, and 1, 1 just x plus y direction.
Oh yeah.
You just apply with loop, and this is just arithmetic Wilson.
Wilson? Okay.
Yeah, just x.
I know people call it Wilson. Okay. I think the intuition is this, but I don't know how to compute this. So
Wilson just the wrap product of the Z poly Z matrix, and you just
Okay. So let's continue.
So you need x1 for the torus. Well, what's x1 is here?
S1 is a ring. So
But torus.
S1 is a ring.
So x1 is just like a periodic boundary condition for one-dimensional.
Yeah. And the torus is S1 product. S1. Direct product.
So the first input should be some pure geometry thing.
Yeah.
Yeah, I understand that the first one is some like geometry and the second one is some like gauge, like the gauge request. So we could output like a ground state, like some ground state with degeneracy type.
Okay.
Even so, I always see this equation in the discussion of topological order. So I always want to know like what's it actually mean.
Okay, now let's continue. So now we are going to introduce the topological defect. This is a very important building block of our categorical description. So, I think there are many hand-wavy arguments here too. So bear with me. And how to say? So we start from a microscopic state, and we know in the microscopic state, so we have some local operators. So what do you mean with local? Local, I think it is something that is very, very small than the macroscopic scale, and when we are going to the thermodynamic limit, it should have upper what it should have below some definite value. Is that accurate? No. So actually, physicists understand the local intuitively. Okay, so there are many local operators such as the sigma z, sigma x, or AV or BP, anything in the torical model. Now, we are doing something called core screening, and it's something like traditionally we'll say it. We are integrating the small length scale, or we're integrating the high energy scales, and to get the low energies effective theories. And when we are doing this process, only the some macroscopic observable survived, and all other things will be, or other local things will be screened by the local operator. So the survived macroscopic things is we call some topological defect. No, it's not say. We should say topological defect is something survived after this core screening. Okay, so this picture says this. So we have a these are all things, these things, sigma xyz, or these plaquettes, or anything. They are all local operators. They're bounded in some finite region, and we have some observable. So when we are doing cross screening, we are doing something like the local operators will screen some local degrees of freedom, and only some macroscopic stain will survive. I think this argument is not rigorous. And
what's observable here? Observable should be some kind of operator too.
You mean some operator?
Yeah, like in quantum mechanics, like
yeah.
we know
So
operator.
So such as here, the very long string of the there's long strings. They are.
So these are
Is this observable?
observable.
The strings is not observable. The ground state degeneracy is observable. We can see that. So.
But that is not what we mean by topological defect. So
Yeah, topological defect. We have something else.
But the ground state is not topological
such
defect.
kind of observable just mean that what you can really see in the non-wavelength limit, like the something that the local operator cannot annihilate.
Oh yeah, yeah.
So ground state is topological defect.
No.
Some trivial topological defect.
Oh. Yes.
So like for a non-contractible loop, it's a topological. It's a non-trivial topological.
Sorry.
So non-contractible loop, right?
Loop. What do you
Yeah,
mean?
just the
Actually, these loops are can't be observed. So
no, it could be observed by using loops.
Such uncontractable loop is some global observable. It depends on the topology of your manifold, but here the topological defect does not depend on the topology.
it can be. Yeah. I mean, we can now use local. You can. Yeah. So I think in the book there is some remarks.
Is there
Illustrating this problem.
so is there any examples of topological defect in topological model?
Yeah,
So in that was
it's going to introduce.
okay.
We were talking about yeah. So and yeah, another concept is the excitation. So how do we describe the excitation, especially in the excitation located around some specific site? So we can say this psi sig how to pronounce this Latin precise psi. Oh, C. This psi C. We can view it as an excitation of the original Hamiltonian, and we can change our view and view it as some as the ground state of some Hamiltonian. Okay, so I know there is some philosophical question about is this some Hamiltonian exist? Okay, so we first assume it exists, and then we write it as something as the original Hamiltonian plus some perturbation. So it can be looked at some local perturbation around the psi. Okay, so actually we will use the second view of point more often. Yeah, so once we see an excitation, we can sim as the extra term as the in the Hamiltonian that traps this excitation. So this is called, this leads to the topological defect. Yeah, so let me see. Okay, I don't write something in here. So actually I was discussing with Xingyu tomorrow. This is something that the excitation is not a good word, because sometimes the excitations is not observable. Is that right? So we use something as defect. Defect is something in the Hamiltonian, this delta H. So something like such as we cut the torical model and give some open boundaries, or yeah, the boundaries will be some defect. No. if you will be defect. Yeah.
This location of the.
Oh, this location, yeah, something like this.
And actually, I think we better do not call the delta H side of perturbation. It's a,
Oh, it can be not small.
yeah. Defect at the reading side, it cannot be a perturbation. So
Oh, yeah. And topological data.
You do more stuff.
So, if a defect is not topological, we may unequal.
没变。
我操，这不是我的问题。
一个特征，并不是一个，并不是一个最本质的特征。有时候
这样比较 tricky，就是
但是对，
那我们想定义一个 topological order，但是我们其实是用了一些它里面的一些 defect 来定义它，但是这个 defect 本身也可以看一个一个低维的 topological order，对，topological order。
操，你那天电脑要删啊！
网上听的人很多嘛，他有些直接讲的。
Not very much. But I think they should feel very bad. Oh, something. So when we are discussing, I think you guys can be louder. Or the microphone not pick it. So what?
直接说吧。
啊，没事，他还在录，但是看不到我屏幕啊。
你可以拿着电脑把这个车上去编写给
你们可以打开电脑，然后上面看，你们就看电脑屏幕。
我没有 WiFi
啊。学校有，这里有 WiFi 的，我
看要什么 guest 什么 ID 什么。
OK，你可以连物理系的，物理系那个有个密码。
有吗？
这一 guess， 直接找记什么吧。G26，没有G26，只有5人，所有的都是原本。
你们就写黑板多好，写黑板挺锻炼人的。
呀，
对，就直接做 note 写黑板，我觉得投影有点。
写黑板主要是有些图可能我在上面画，
都是这样的，国外都是这样的。
Yeah，
国外没有，基本上不会统一的。
而且写黑板进度要慢一些，就是提前写。
这个讲得清楚啊。
Okay, so we fix this problem.
屏幕了吗
Recording. It's recording. So, so just now we said that an excitation is not a good word. So it's something that is hard to detect. But then a defect is a thing that we can measure directly. easily, okay? So can you repeat your argument again? Yesterday?
Like the defect is something we can add some like local terms or dislocations to traffic
Yeah. I should write it.
expectation. So first the topological order is the gap system along not the limit. So actually when we say expectation it's does not make much sense since in the long wavelength state only the ground state survives. Right. So I think we so the topological defect is makes more sense than the than expectation. But so the ground state of the H plus delta H flat sometimes it's just expectation state in of the original Hamiltonian. So something we also say is a topological excitation. But I think topological defect data is more
Yeah.
kind of
Physical. Yeah.
I think all the string diagrams in the category series are in some sense semi-classical viewpoints. So when we detect something, we are doing the semi-classical some observation.
Drag it
So,
around.
so the excitation is not semi-classical.
What do you mean by saying semi-classical?
For example, we can modify the Hamiltonian by our some experimental technique by
Yeah.
adding some other atoms to it. And this can be modified by our external devices. And so when we say the trajectory of the anion, we cannot say it in the quantum mechanics viewpoint. Because the quantum mechanics does not have the trajectory. So the string diagram in the category is some semi-classical description. So the delta H psi here is just the extra potential. This potential is the classical one in some sense because we can fix the size. We can do it classical.
Yeah, I have another question. So what do you mean when we are saying for braiding? So braiding is some particle flying around. So if they don't have trajectory.
Yeah, so that's why we are talking about defect rather than the excitation.
Okay.
I still don't understand, but I could like in experiment, I could use like STM or some kind of ion atom to to get the localized Hamiltonian. But why do you say that it's classical?
Sorry.
So why do you say that local Hamiltonian is classical? We could
Because it is changed by our experimental methods, and that is possible.
Yeah, so for example, like we have an E particle on vertex and we rotate it along some trajectory. So so this process can be done like if we do a adiabatic transformation of this delta H psi. Like we can change this psi along this path. So the anion just change
Yeah.
But if we excitation,
We cannot say the excitation is weird.
yeah,
Is what?
Weird. 在哪？ Okay, okay. So, the topological defects is something like this. So we can deform the lattices to get something. This is a dislocation, and I think this is a vacancy of a vertex of a link. Okay, so and here's another definition. I think this definition is too math anyway. So we just say that the topological excitation or defects survives from the local operators screening. So if give a topological excitation like this psi, and when we act some local operators, so we just said that the local operators do not screen this. So when act some local operators, it should also remain this topological defect. Okay, so so here we define a subspace of the Hamiltonian, and the subspace is that given a precise state topological defect, it can be same as, and we act as all kinds of local operators are met, and it will give a subspace, and we think this whole subspace is this topological defect. Anyway,
It's just like quantum error correction. During quantum error correction, you just like create some subspace out of a full Hamiltonian. So here you have related a given topological defect to a subspace of Hamiltonian.
Yeah. So I think it's reasonable, but it's not so intuitive.
That's just like a stabilizer. You apply like local operators to the topological defect, and you get you just the end value is 1, right?
Okay.
The a phi equals to 5, right?
no,
No.
yeah.
But actually can be not so may not be the ground state. It can be an excitation.
So if A is local operators, A apply on phi. So what's the result? Is that phi or?
How do I say? So I think the Zhihao want to argue that so physically, when we act local things on the topological things, the topological things should not change.
So it should be.
So
phi.
we pick up all the subspace of the local of these things. So we use the local operator, all kinds of local operators. We act on it, and we say this should not be changed. So it should form a subspace. It's something that's
not changing.
You take A1 side plus the A2 side, okay, and you can attract A, and then it becomes A1 plus A2 and bracket side, and A1 plus A2 is a still local operator.
No, I just want to ask, like A apply on phi is the result of phi.
No, so I think the point is we are defining something macroscopic.
This is the invariant subspace.
Okay, then notation, you take a state psi, and if you have a space of local operators, you act all the operators of psi and a bunch of state and collect them together at a set form of subspace.
Ah, I see.
okay. And
So could I understand like the all local operators as stabilizer?
Um,
It just, you mean subspace here, subspace just reminds me of quantum error.
yeah,
correct?
the torical is a stabilizer. So,
Yeah.
here is hard to say. It's hard to define what is local operator. It depends on the size, on region. And you have to specify some local region.
I see. Yeah.
Okay, one example is that this trivial topological defect is generated by ground state. And here is related to your question. So we can see that the ground state have 4 different states, but they all denotes to the trivial topological defect. Okay.
Why do you see that is trivial?
Because this is ground state, there is no excitation. Okay.
Actually, like, if you add some local operator, you cannot change from the side 0 to side 1.
Yeah.
So I think here we better not talk.
Use this example.
Yeah, or you can just say we do not consider the geometry of the manifold. So
Yeah.
then they are just one ground state, and all the local operators act on the ground state. Then
Gives to the cross the trivial topological defect. Yeah.
subspace is the-
Oh yeah. Okay. It's a good understanding. And here is some topological excitations. So here it may, it is excitation, not defect. Okay. Let's follow the book. The first excitation is the E particle. So it says that intuitively it's the end of the AV operators. Say we see the V0 in this graph, and so it satisfies some equations. Okay, let me see. Why Shihao write down these equations? He want to use this to define each particle.
Yeah. So it's just
So we
so the A B 0 is -1, and the other equation +1.
Oh, the definition of the E particle. Okay.
The particle on B 0.
Okay. So it's defined as this, and then interesting observation is that we can move the V0 excitation to the V1, use the sigma Z operators. So remember that AV is made by sigma X, and we are using sigma Z here to flip the sigma X, and to this is easy to check, and please continue. I can't see the question.
Can you hear?
Share screen, share the application.
Can you hear?
What? Sorry. Can you be louder?
Okay. Can you hear me?
Oh yeah.
Oh.
Okay.
Here I have a question. Should this E particle always appear in pair? I mean, here you just define a position V0 in which we have a E-like particle, but should this particle always appear in pair?
Yeah, it should. Remember our constraint. Remember our constraint on the closed manifold that all the AV operators times together should give to 1. Remember that?
Yeah.
It's here. Let me. This constraint, this. All AV operators times together should give to 1. And this is not a constraint on the ground state. This constraint is on the whole, on all kinds of states. There should be 1. So when you have an AV equals to -1, you must have another AV equals to -1. So this E particle should be created by with pairs.
Okay, thank you.
Yeah. Okay. 是兼容的。
No, actually,
在这里 close manifold 上。
Oh yeah, close manifold. Yeah. So when we have an open boundary, we may create some we may create these particles from the boundary and move it to the box alone. So we will talk about this in the later chapter, but it is a little far. So we'll come to that.
Here, the reason that we didn't write inside because we are talking about the R of the another end of the E particle is very far away. Okay, so if we only focus on the local size, so we can omit the single E particle.
So can you hear me? So sorry for that. There's some problem in my internet. So okay, let's restart. And here, what do I want to say? Yeah, in this part, we want to say that I want to show that when we act on this sigma z, actually this we denote as a sigma z1, and we will move a v0 e particle to the v1 side. Okay, so it is easy to show because the sigma z is anti-commute with the sigma x. Okay, so so this 0 have a sigma x anti-commutated with it, and this V1 has a sigma x anti-commutated with it. Okay. So, and in this situation, the delta H equals 2 MV. So, show this. Oh, QAB. I'll show this. I think it should be in the book. It's right in this form. Let me see this. Yeah, it writes this form. It is an extra term of 1 plus AV0 because AV is -1. Okay. But we should have another V equals to -1. So we should have another V equals to -1. We should have a pair of 1.
Most meaning for this term should be 4.
No, two AV and plus 2 AV, some AV, some other AV.
That all AV, the times of all AV equals 1, just the counting of the closed manifold. So if you just consider the model locally.
Locally. Okay, yeah. It's the argument that we said just now. Okay. So locally we have a 2 AV0. And it's similarly for the M particle. It's the M particle lives at the end of the plaquette. The plaquette string. How to say this blue one? So this string is the it's a little different. It's this blue line is sigma z, and we have a string of sigma z like this, and we connected them as a string like in this way. So you can understand it intuitively. And here is another interesting particle is that if we put these two E particle and M particle together, it's something we call fusion, we will get an F particle. So we will get to the fusion in a minute. So and I have some questions. So how do we find a complete set of the excitations? Say for give us a Hamiltonian or give us a model. How do we get a complete set?
You mean
So how do we know this is complete? We have 4 excitations. How do we know that they are complete in this model?
You have to use 3 here and by 1.
And we have 1 trivial one.
What is trivial one? Identity?
Yeah, it's just generated by the ground state. So we do not, and there is no defect.
But why could you say that is an excitation? That
It's the trivial excitation.
It's just counting if you want to count 0. C++, yeah, different information of counting this mathematical dimension. They want to count trivial thing as something.
yeah, yes.
So
I don't know, maybe you should maybe we'll just add some other terms to the Hamiltonian to find that the particle effect can always be expressed as a direct sum of the one.
okay. So another question is I ask it tomorrow. not tomorrow, yesterday, but but we don't have a good answer. So how do we understand the direct sum? So it's like 1 plus n, so something like this in a physical way, so intuitively.
So far, I haven't.
Oh, in the book we have some. Yeah, let's come to the book. He has some arguments about the. Yeah, he added a term, and let me see. Oh yeah. Add BP, yeah. He added only 1 BP. This term, he added only 1 BP, and he says that this Hamiltonian generates the 1 plus n. You say it should be 1 minus BP, so it add BP, so it become 1.
So in this the BP can be either the minus 1 or plus 1. So it's generally is large. So
Yeah,
the
two will be
direct sum of the one trivial fraction in the original point and the direct and another subspace that n is accepted. So it is the direct sum of the two subspace of originally the simple of S. So this direct sum comes from the direct sum of the lengths.
Yeah, so we know it's some direct sum in the fact, but we don't know how we can view it in intuitively. So because we have fusion, the fusion is something you move the 2 particles together, fuse together. I don't know, so give me an n particle. How can I transform it to the 1 plus n particle and something like this?
So mean that you add a BP here and separate the original, the table space to like 2 parts.
Yeah.
And just direct sum there.
With this symbol, the 1 and m here is the equivalent class of the Hilbert space.
Yeah.
So the direct sum here is also from the Hilbert space. So after some equivalent class is mode.
You add up subspace. Putting 2 subspace there.
Right.
So 1 direct sum m here could equals to the original table space.
You can translate it into the vector space direct sum to m particularly set this space. I think superposition because everything comes from
Typically, it's superposition. Pretty speaking, no.
How I can have subspace. Superposition. Means it can be 1 or it can be n. Depends on measure. Oh yeah.
Maybe if you measure the state, you'll compare. Yeah, this state is not stable.
Oh yeah. I read that.
If you just modify BP at that side a little bit, it will collapse to either n or either 1, right?
So in the experiment, so we want to detect this excitation. So what do we get finally?
You don't really get it.
No.
You only get a stable 1 or stable n.
So we can't measure this.
You can measure that, and if you try to put some local measurement there, usually this direct sum will split, kind of collapse to one of the toys.
So it collapsed. So how do I know it is 1 plus n?
And do matter measurement and some random perturbation gives you different outcomes.
Oh, yeah. Good. Good. Okay, let's continue. And I think the time is let me see how many things we have. Maybe we can start, we can stop here. 我不想讲那么久。其实我觉得1个半小时已经很长了，而且我们没有任何的 break。
这个网站我就上去看下去了，刚好就看到 external 的，这是 external 对，所以可以介绍一下。
我
因此嘛，
external
电脑就是一个在
我马上就会讲，我马上就会讲，来，我把这里讲。OK， 继续吧。我觉得下次大家还是控制一下，就是尽量在1个半小时。然后我们可以再讨论一会儿，可能就差不多9点半了。Okay, so instanton we can view it as a defect. So remember, such as in 2D, the space dimension is 2, and we always have one time direction, and we picture this thing as this, and the basic idea is at a point it can be a defect X, and sometime later it may become another defect Y. So yeah. So there is a transition between the X and Y and in the time direction. So the position is not, it is fixed. So it just transformed to Y at the same position at some time. And upon some perturbations, and we denote this, we can see this as a defect, as a 0 defect. So so in the lower we have defect X, and in the upper we have a defect Y. They are all one-dimensional in time, so we have a 0-dimensional defect, something like this. Okay, we denote it as F in home XY. So we'll explain it later. So home XY is the language of category, and anyway. So
what's A?
what?
A.
A?
The picture A.
Yeah. A is the process of the screening. So
basically just operator.
so many operators. So
Mentioned before.
Yeah.
For the
And
space.
you can view B as some cross-grained results.
Operator.
Yeah. So here we want to show the mass structure. So the category structure from some physical intuition. So how to say? These notations are all from category theory. So it says that it is the figure 12. It says that so if we have 2 instanton, and we can move it in the time direction and collapse. So we collapse Y, and we will finally get some instanton between X and Z, and how to say? Should they equal? Yeah. It's equal, not Can we have any face here of this map? Come. So, do you remember that in the associativity diagram, we do not require them to be equal. We require some map here up to a face or up to what?
I think here, it just means that the cross graining or the fusion of two instantons is just like the composition of quantum.
So why it does not introduce some extra face?
Because they are just two instantons.
Oh, you see.
It's defined by the.
I mean, if you have another instant H compose G and first and the like, it's isomorphic to G and F compose first and then compose to H. So there may be some isomorphism.
Yeah, it's up to isomorphism. This so why this is not up to the isomorphism?
The computation.
Why?
You don't have room for isomorphism.
Oh, it's
This the highest level, everything is straight.
okay.
Just operator composition is straight.
Okay, it's a straight.
So could I understand this picture as the two E particle photoelectron they combine?
Yeah, they can
So
combine.
is this the same thing? As this?
Yeah.
No.
Oh,
This is the timeline.
yeah. That is the position.
What's the difference?
That fusion. That's fusion.
Mathematically, not the same.
So that the whole entire line X that and replace X to E.
Yeah.
So you're thinking about two even component is like two lines going together.
Oh, I see.
You have an extra dimension, so
Uh,
there the associativity is not straight.
Here it means you have that E, and at some time it becomes E or it becomes M.
will this really happen? Physical words or just
So you can just see those operators.
over it?
Yeah.
I see.
Some operators,
So we just
Oh, I see. So just like
some change in time,
I see. I see.
but screened by local operators.
we just said that 1 plus M can be perturbed to 1 or M. So this, I think this is an example.
Yeah.
Okay, another is associativity. That means
It's maybe one more question. So will it like related some like dynamically, that the quantum dynamics, like because it's like time evolution, like we add some like quantum gates. Do we understand in that way?
Yeah, if you think about quantum circuits, then those have morphism are just quantum gates, some evolution. But here we are considering topological phase, so we do some grading, local grading, grading by all local operators, so they only some the local thing left.
Oh, I see.
So it's very coarse-grained description.
Yeah.
okay. The associativity, the aim of associativity is to require that we to make sure that this product has no ambiguity. So and I think we can prove that. So if the associativity of 3 instanton holds and any number of instanton should hold. Yeah, I think it should be. And finally, there is identity. Identity means that we can do nothing in the timeline. So, and how to say this? So, it's basically the 2 pictures down here. So we can do nothing in the for an instanton from X to Y. We can do nothing in the Y region, and we can do nothing in the X region. So here we should notice that this product is not true. This product is not commutative. Commutative, yeah, it's not commutative, so you cannot swap it. Okay, so these things observed, these structures observed above gives the definition of the category. So it's I think we'll leave it to tomorrow. Okay. So is the Anna is not so good, Billy. Where do
那个体感和体它们之间的 build 是 momentum 之间的稳定momentum 或者 operator 之间的那个。但是就是说，你一个空间上有的话，你在时空上它其实是一条线。对，对，但是这个就是时空里面在这个它真的是一个时空里面定位的一个地方。其实我想想这个就是这三线里面的操作。到底是什么？是在 physical two 要说你觉得是加one they have exactly the same 像这个包括 physical OK 要咱们这三地方对弄一个往就是发生我们保护它变成一了比如说3比如说你把加上一项结束还放在时间上它的 different 所以你说的是它刚出来的这 semi graph 这挺奇怪的，为什么这么长？明白你意思了，所以我现在终于理解了你说的对。
Self space. There's no kind of like